Hey guys, welcome back. This is the last video in Chem 1 here. Kind of exciting. This is all problems. So my recommendation is to do the problems and then come back and make sure you're right. That would be my recommendation as always. And I love these problems. This first one's top 5. All these problems I stole from Michigan State. I love them. They're great. So I don't remember if it was Dr. Hunter who wrote them or not, but this one and then the next few are from a test. And they're great. All right, so let's dive in and go with that. So this is the gas stoichiometry. And we have two gases shown. On the left is nitrous oxide. On the right would be oxygen gas. And you have their pressures, you have their volumes, right? And they're connected with your tap. And we're going to say that tap does not have any volume. We're just going to ignore the volume there. What's nice is we have the temperature is constant, all right? Which again, after amount of time is not a bad assumption. Obviously the temperature changed during the reaction, but all right, let's go with this. So we got these guys are going to mix, make as much product as possible. All right, there's 3 questions. How much product is available? How much NO2 is available at the end? What's the partial pressure of whatever one's left over? So whether it's nitric oxide is excess or oxygen is excess. One of them will be excess. We want to know what that one is, the pressure is. And then we want the total pressure. So if we were to ask just 3, we'd have to do 1 and 2 first to get to 3. All right, so let's look at this. Let's come up here first. So before the reaction, we open and we're going to mix, right? And so before reaction, open the valve. There's a mix. That's a new volume, all right? PV equals nRT. Well, temperature's constant. R is constant before the reaction. So this is no change yet, which means we're right there. PV, right? Since the volume changes, the pressure changes. So we're going to have P1V1 equals P2V2 over here. And we're going to have P1V1 equals P2V2 over here. All right, let's look at N2O first. I have 3 atmospheres. I have 3 liters. P2 times 3 liters and 2 liters is 5 liters. So divide both sides by the 5 liters. It looks like I got 9/5. For O2 here, I have 5 atmospheres, 2 liters, P2, and 5 liters. So divide. So that would be 2 liters, or sorry, 2 atmospheres, or I'm going to put down 10/5 atmospheres. It's really 2 atmospheres, right? And so if you're that way, go ahead and do that. If you want to use the whole numbers and 1.8, and so if you wanted to use 1.8 atmospheres here, you can. How about I spell it correctly? There we go. So if you wanted to do that, you can. I'm going to use the fractions because I think the fractions are easier and faster. All right, I'm going to rewrite my equation. N2O plus O2 going to NO2, and we have our 2, 3, and 4. All right, and we have 9/5 atmospheres, and we have 10/5 atmospheres. All right, we have to do a limiting reactant now. And so However you want to do this, 9/5 divided by 2, or 9/5 divided by 2, and 10/5 divided by 3. And so because of this, here's how I'll do it in the fractions. 9/5 divided by 2. 9 divided by 2 is 4.5. And 10/5 divided by 3. 10 divided by 3 is 3.3. And so that means oxygen is my limiting reactant. Now, if you don't want to do that, if you wanted to do 1.8 divided by 2, give you 0.9, and 2 divided by 3 to give you 0.67, not 6.7, 0.67. You could do it that way too, right? If you do the whole numbers. Again, that's your preference. All right. We know this is gone now, and I'm going to start with that one. All right. So oxygen is my limiting reactant. We're going to have 10/5 atmospheres of O2. And we're going to go with what? We're going to go with 3 atmospheres of O2. Produces 4 atmospheres of NO2. And if we do that, I'm going to get 40/15. If you wanted to reduce it to 8/3, you could. Or 2.7. All those answers are fine. All right, so that's how much NO2 we make. All right, then we start with our 10/5 atmospheres of O2. And what am I doing now? So the first, let's just write this out. 1 was product. 2 here is excess reactant. How much N2O is left over? All right, and so we're still going to have our 3 atmospheres of O2, but we have 2 atmospheres of N2O up top. And that's going to give me what? 20/15. That's how much we use or we consume. Which, if you reduce that, that's 4/3. Or 1.3. So that means if I start with 9/5, well, let me give you some more space down here. We're going to start 9/5 atmospheres of N2O, and we're going to subtract 20/15. All right, now, again, this is also 1.8 and 1.3. So now it depends on how you are with math, right? It does not matter to me. 9/5 to 15ths is 27/15. And so you're left with either 7/15 atmospheres, or you're left with, what is that, 0.5? Yeah. All right, which 7/15 is not quite 0.5, right? So one of the other things I like working with fractions is you're not rounding, even though you're still using sig figs. It's kind of fun. All right, so now the total pressure. Right, our 3 species. We got O2 is 0 because it's the limiting reactant. We have either 7/15 atmospheres, or you might have had 0.5 atmospheres here for N2O. And our product, we had either 40/15 or we had 2.7. So that means my total pressure is either going to be 47/15 or would be, what, 3.2. Now, 47/15 is actually 3.1. All right, so that's just different, but that's okay. For me, either one of these is fine. I'd be happy either way if you did it. All right, so that's how we do the two gases mixing. All right, next one. 8-liter vessel contains 5 moles of hydrogen gas. Let's use here 5 moles of hydrogen gas, 3 moles of helium gas, and 2 moles of oxygen gas at a pressure of 25 atmospheres. What is the temperature of the gas? Well, we have a PV equals NRT here, it looks like. Oh, I missed the 8-liter vessel. Didn't highlight that. All right. And so our pressure is 25 atmospheres. Our volume, 8.0 liters. N, well, all of it, right? I got 5.0 moles plus 3 moles plus 2 moles. R, 0.08206 liters, atmospheres, moles, Kelvin, and we don't know what T is. All right, so that means it looks like we have 10 moles total, don't we? All right, that's what it looks like we have. All right, and so if we were to do this, the temperature would equal our 25 atmospheres, our 8 liters, divided by our 10 moles, and our, it's actually 10.0 moles, isn't it? And our gas constant of 0.08206 liters, atmospheres, moles, Kelvin. So if I do that math, right? Okay, 25 times 8 divided by the 10 divided by 0.08206, I get 243.724 Kelvin. Now, I get 2 sig figs, so 240 Kelvin is our temperature. All right, there we go. Number 2, what is the partial pressure of oxygen gas? That's the question. What is the partial pressure of oxygen gas in the mixture? So everything else is above. Well, partial pressure, the pressure of O2 would be equal to the mole fraction of O2 times the total pressure. Right? That's Dalton. Dalton's partial pressures, right? Well, now I need to get the mole fraction. Well, the mole fraction would be what? Moles of O2 over total. Well, it looks like there are, what, 2 moles of O2? If we go back up, 2 moles of O2 over 10 moles total. All right, so 2/10 or 1/5. All right, and the total pressure is from above 25 atmospheres. So now we can do the pressure of O2 is 2/10 or 1/5 times 25 atmospheres. So that would be 5.0 atmospheres. Excellent. Because technically this is 2.0 moles, right? 2.0, 10.0. Well, so 5 atmospheres. Excellent. I like it. Hopefully that makes sense. Now, number 3. Suppose that an additional 7 moles of hydrogen is added to the mixture. So, all right, now we have 7 moles of hydrogen is added to the mixture, which means for hydrogen, if we look at hydrogen, I originally had, you gotta go scroll back up, 5, right? So that means I have 5.0 moles plus the 7.0 moles. So that means I have 12 moles of H2 without changing the temperature or the volume. So that means, all right, we have without changing temperature or volume. So that means they're fixed. What is the partial pressure of oxygen in the new mixture? All right. Wow. What do we do here? Well, let's look. If I do let's just do black. PV equals nRT. We are not changing the temperature or the volume, so they're off the mark. R is fixed, never changes. And so if we look at this, we are definitely changing N, aren't we? We're adding 7 more moles, which means what has to change? P has to change, right? So this has to change. We add here, so this has to change. Hopefully that makes sense to you. All right. So now we can just go P equals nRT over V, right? We can do that. So if I do that, P equals N. Now N is what? It's 17 moles, right? 17.0 moles. R is 0.08206 liters, atmospheres, moles, Kelvin. We have 240 is all we get Kelvin, 240 Kelvin, right? Because with sig figs rules, even though 244 would be better, but it's only 240 Kelvin. And then I have 8.0 liters. So that means the new pressure is going to be what? Let's take it 17 times 0.08206 times your 240 and divided by 8. I got 41.9 or 42. 42 atmospheres. All right. So now we can go back to P of O2 equals the mole fraction of O2 times the total pressure. So our pressure of O2 would be the mole fraction. I still have 2.0 moles, but now we have 17 moles total times our 25 atmospheres. So that means my pressure of O2 would be what? 2 times 25, which is 50, divided by 17. Not 25. Sorry, guys. That's not 25. It was 25. It's now 42. So let's try that again. And I get 4.94. So I get 4.9 atmospheres. Now, how does that compare? There. 5 atmospheres. Let me ask you a question. Did oxygen change? Right? Did we add any oxygen? Did we take any oxygen away? The answer is no. It did not change. Right? So we spent some time here. We got 4.9, and 4.9, that's due to sig figs. Because if we use 244 Kelvin, we'd have got, just so we all know, if I use 244 Kelvin here, I get 42.5 atmospheres. And if I do 42.5 atmospheres, I get 5.0. All right? And so it means oxygen doesn't change. The pressure of oxygen is still 5.0 atm. And the reason it did not change. And so why I like this problem so much is not that we have to do all this work to get there, because there could have been things we did differently. What I like about this is that if you realize that oxygen didn't change, this is a 30-second or less problem. All right? And so that's just, I like how it tests our understanding of the gas laws, because we recognize that oxygen didn't change. I don't need to solve anything. I need to realize that it's still 5 atmospheres because the volume and temperature are constant. All right? That's why I like that problem. So it's still 5 atmospheres. Now, in the next problem here, number 4, what are we adding? We're adding 4 moles of oxygen to the mixture without changing the temperature volume. So now what is the partial pressure oxygen in the new mixture? All right. Well, now we're changing oxygen, right? And so we could do a PV equals nRT, right? We could do this. We could do PV equals nRT. And now with 4 more moles, we're at 21 moles, right? We could do that. However, if we go P times V equals N times RT, right? We know that that's constant, and we know that that's constant, right? So that means pressure is proportional to the number of moles. Does that kind of make sense, hopefully? Right? It's directly proportional. So I do P1 over N1 equals P2 over N2. We know that the first pressure of oxygen was 5.0 atmospheres at 2.0 moles. All right, we knew that. And now we're adding 4 plus 4. So that means the new moles is 6.0 moles. What is P2? Well, what do? Well, sometimes it's a times 3, so, but we cross multiply, or all you have to do is take 5 times 6 moles to both sides. Times 6.0 moles, 6.0 moles, times, so 6 times 5 is 30, divided by 2. P of O2 is now 15 atmospheres. All right. So hopefully that works out for you guys. You see that relationship, that pressure is proportional to moles there. Now, number 5. Here it is. The mixture after the 7 moles of hydrogen. So that means now we have 12 moles of H2, right? Because you started with 5.0 moles. And we added the 7.0 moles, right? And oxygen, 4 moles of oxygen. So we start with 2.0 moles. We had the 4.0 moles. So that means we have 6.0 moles of oxygen. Is now ignited to form water. Okay. So we have H2, gas, plus O2, gas going to H2O. And then it says the mixture is cooled to the original temperature of 240 Kelvin, which, just so put that in perspective, 240 K, right? What temperature is that in Celsius? All right. Did you ever think about that? So minus 273, right? Minus 273. That gives us negative 33 degrees Celsius. And so chances are the water is not just going to be a liquid, it's probably going to be a solid. But we're going to put down the cool to, and the volume doesn't change. The water condenses, we're just going to put an L down because of the temperature. All right. But if you wanted to put an S down, that's probably a wise choice too. The water completely condenses. The question is, what is the total pressure of the gas in the vessel? All right, is my equation balanced? No, I need a 2 here. Oh, that's a highlighter. Sorry, guys. I need 2, 1, 2, right? That's hydrogen and oxygen going to water. We have 12.0 moles of H2, and we have 6.0 moles of oxygen. What's the limiting reactant? Well, 12 divided by 2 is 6. 6 divided by 1 is 6. So that means they are both present in the correct ratio. It means they are both 100% consumed in chemistry land. So that means there's none. So that means we make 12 moles of water. All right, and there are 0 of that. So does that mean everything is gone? No, right? Still have what? We still have 3.0 moles of helium. We have 3 moles of helium. Now, did helium ever change? And that answer is no, right? We didn't add any helium. We didn't subtract any helium, right? So we can go back to the original. All right, pressure helium. It's the mole fraction of helium times total pressure. So the pressure of helium is equal to the mole fraction. We had 3 moles of helium, right? Over 10 moles total times 25 atmospheres, right? That was the original pressure. So that looks like it was 7.5 atmospheres of helium. And there we go. All right. So those problems, I like those problems. And so that shows you the gas laws and how we can kind of like look at their relationships to each other. I kind of like that. All right, next one. What is the density of argon? There's your question. What is the density of argon? All right, it has 1 atmosphere of pressure, and the temperature is 25 degrees Celsius, which, of course, is plus your 273. That's 298 K. Well, if you remember, the density of a gas is going to be equal to what? It would be the pressure times the molar mass divided by R and T, right? And so the density, pressure would be 1 atmosphere. Molar mass of argon, I got 39.95 here. Grams per mole. R, of course, is the 0.08206 liters atmospheres moles Kelvin. And our Kelvin is 298 K. All right, and a good check. You can always look, do our units work out? All right, so let's look at that. Do our units work out? Atmospheres is gone. Moles is gone. And kelvins are gone. And so I'm left with grams over liters. Yes. So that means our density, we do the 1 times 39.95 divided by 0.08206 divided by 298. I then get 1.63 grams per liter. All right. All right. Last one. And I like this problem as well. You have 5 grams of manganese. All right. We have 5 grams of manganese metal. All right. Highlight that out. 5 grams of manganese metal is reacted with excess HCl gas to produce 8.63 liters of H2 at that temperature and pressure, and a manganese chloride compound, MnClX. What is the formula of the chloride compound? Oh, wow. Okay, so we have manganese, Mn solid, plus HCl gas, going to H2 gas plus MnClX. And that's probably going to be a solid. We went on X's. All right, so I look at that reaction, and I don't know if I can balance it because I don't have X. What I do know is I have 5 grams, or we have 5.00 grams of manganese, and we know that we have, 8.36 liters, 373 Kelvin, and 1.00 ATM. And we have excess. All right, so what do we do here? What type of problem do you think this is? I think this is a conservation of mass type problem, but with gas loss. All right? So I can go from 5 grams of manganese, right? We know manganese is 54.94. And so if I do 5 divided by the 54.94, I get 0.0910 moles of manganese present, right? And that's my limiting reactant. So I know my limiting reactant, right? Because that's HCl's excess. I don't know how much reacts. However, I know how much H2 is produced, don't we? Okay? And so if I know how much H2 is produced, I can use PV equals nRT. I know the P, right? I know P, I know V, and I know T. And of course we know what R is. So I can figure out N. N is PV over RT. So P, 1 atmosphere. V, 8.36 liters. R, 0.08206 liters, atmospheres, moles, Kelvin. And T is 373 Kelvin. So it looks like number of moles of H2 is 8.36 divided by 0.08206 divided by 373. I get 0.273. 0.273 moles of H2. Now, what do we notice? All of the H here, hopefully we notice, all of our H, right, that's our key. Right? All the H came from HCl. However, what do we know about this? There's a 2 here, right? So that means the mole ratio would be what? How did the moles ratio? I would need 2 HCl's to make 1 H2. Now, do we know that it's a 2 and a 1? No. But we know it's 2 to 1. So could it be 4 to 2? Could it be 6 to 3? Whatever it is, HCl has double the coefficient of H2. It just has to work that way because I need 2 HCl's to produce 1 H2. All right. And because of that, I'm going to take our 0.273 moles of H2 and moles of H2, moles of HCl, right? And we know that it's going to be 1 mole H2 to 2 moles of HCl. And then I'm just going to write this out that 1 mole of HCl has 1 mole of Cl. So that means if I double, I get 0.546, 0.546 moles of Cl reacted. So when we take our MnCl compound with X here, we know that in our compound we have 0.0910 moles of manganese and 0.546 moles of chlorine or chloride. Well, I don't like those numbers. It's the right ratio. We better make them whole numbers. And how do we do that? Divide by the smallest. 0.0910, 0.0910. And so we get 1 for manganese, and it looks like I get 6 for chloride. So my compound becomes MnCl6. All right, so there's a lot here. There's the not a limiting reactant, there's the law of conservation of mass with the gas law and empirical formula. I like this problem. It's a good problem. All right. And also good about this problem is that there's not more than one answer, right? Because there's more than one manganese chloride compound. So that's great. Well, that's it, guys. If you have any questions, feel free to reach out. Otherwise, we'll see you next time. Take care, guys. Goodbye.